Imagine standing beneath a perfectly dark sky, far from the glow of city lights, where the Milky Way stretches overhead like a river of luminous fog. Billions of stars shimmer in that celestial band, each one a sun with its own story, its own family of worlds. Yet, for all their brilliance, for all their collective light painting the night, they are all servants to something unseen, something so massive, so utterly dominant, that it commands the motion of every single one of those distant fires. At the heart of our galaxy, hidden behind veils of dust thicker than the walls of any fortress, concealed within clouds of gas and the glare of a billion suns, there exists an object of such profound darkness that it defies the very nature of light itself. It possesses no surface to land upon, no atmosphere to breathe, no light to reflect. It is a wound in the fabric of space and time, a gravitational abyss from which nothing, not even light traveling at 282 miles per second, can escape once it crosses the threshold. This object is Sagittarius A, pronounced Sagittarius A star, the supermassive black hole at the center of the Milky Way. It weighs as much as 4 million of our suns compressed into a region smaller than the orbit of Mercury. Every star you see in the night sky, including our own sun, that life-giving furnace 93 million miles away, moves in a grand cosmic dance around this invisible choreographer. Our sun, along with all the planets, completes one full orbit around the galactic center approximately every 225 million years at a speed of roughly 514,000 miles per hour. We are all, in a very real sense, falling endlessly around this dark heart. The paradox is striking and humbling. The most massive object in our galactic neighborhood, the gravitational anchor for hundreds of billions of stars, remains completely invisible to ordinary observation. It neither emits light nor reflects it. It devours both with equal appetite. And yet, through decades of patient observation, ingenious measurement and theoretical insight, we have come to know it intimately, to measure its mass, map its influence, and even photograph its shadow against the glowing matter that swirls desperately around it. What we have discovered challenges everything we thought we knew about the fundamental laws that govern reality. The black hole at our galaxy's center is not merely an object of astronomical curiosity. It is a laboratory where Einstein's most radical predictions about the nature of space and time are tested to their breaking point. It is a window into physics at its most extreme, where the familiar rules of our everyday experience crumble and new, strange principles take over. Before we venture deeper into this cosmic abyss, let me pause for a moment of clarity. What you're about to read isn't speculation, science fiction, or philosophical musing. Every claim, every description, every startling fact comes directly from the work of astronomers, physicists, and researchers who have devoted their careers to understanding the invisible heart of our galaxy. The telescopes are real. The measurements are published. The observations have been replicated and verified by independent teams across the world. If you find value in thoughtful science told with care and attention to detail, if you believe that understanding our place in the universe matters, then consider subscribing. Your support allows us to continue exploring these profound questions, to keep translating the language of physics into stories that reveal the beauty and strangeness of the cosmos we inhabit. Now, let us return to the darkness at the center of everything, because at the heart of everything we can see all the stars, all the nebulae, all the spiral arms of our galaxy, lies something we can never see directly. The black hole, Sagittarius A, the gravitational monster that has shaped our galaxy's structure and evolution for billions of years. And what we've found there challenges everything we know about space, time, and the laws that hold them together. What we've discovered at the edge of that darkness has forced us to confront the limits of human understanding and peer into realms where our intuitions fail and only mathematics can guide us. This is the story of how we found the monster at the center, how we measured it, photographed it, and learned to read the signature it writes across the cosmos. This is the story of Sagittarius A, the invisible heart of the Milky Way. When you look up at the night sky, the stars appear frozen in their positions, eternal and unchanging. The constellations that guided ancient navigators look essentially the same as they did thousands of years ago. To the casual observer, the heavens seem still, painted on a vast celestial sphere that rotates sedately overhead. But this stillness is an illusion, born of vast distances and human timescales. Every single star you see is in motion, tracing elaborate paths through three-dimensional space at speeds that would leave our fastest spacecraft hopelessly behind. Our sun, that seemingly steady beacon in our daytime sky, is racing through space at more than 500,000 miles per hour, carrying Earth and all its inhabitants along for the ride. Yet this isn't random motion. There is order to this cosmic choreography, a pattern to the dance. All of these stars, every single one of the estimated 200 to 400 billion stars in the Milky Way galaxy, are orbiting a common center of mass, the gravitational heart around which the entire galactic structure pivots. The Milky Way is a spiral galaxy, a vast pinwheel of stars, gas, and dust, stretching roughly 100,000 light-years from edge to edge. From our vantage point, about 26,000 light-years from the center, we see our galaxy edge on as a band of light crossing the night sky. But could we somehow step outside and view it from above? We would see its magnificent spiral structure, great curving arms traced out by brilliant young stars and glowing nebulae, all rotating around a bright central bulge. This rotation poses a fundamental question that puzzled astronomers for much of the 20th century. What holds a galaxy together? The answer might seem obvious at first. Surely the gravity of all those billions of stars pulls on each other, creating a collective gravitational field that binds the galaxy into a coherent structure. The stars orbit because they're falling toward the center, but their sideways motion, their orbital velocity, keeps them from actually falling in, just as Earth orbits the Sun without crashing into it. This explanation works beautifully for our solar system, where the Sun contains 99.86% of the system's total mass and utterly dominates the gravitational environment. But galaxies are different. The mass is distributed throughout the structure, not concentrated in a single central object. Or so astronomers initially thought. When astronomers began measuring the orbital velocities of stars at different distances from the galactic center, they discovered something profoundly unexpected. According to the laws of physics as understood through Newtonian gravity and general relativity, stars farther from the center should orbit more slowly, just as the outer planets in our solar system orbit the Sun more slowly than the inner planets. This is basic orbital mechanics. The farther you are from the center of mass, the weaker the gravitational pull, and the slower you need to move to maintain a stable orbit. But the observations showed something different. Stars at the outer edges of galaxies were moving far too fast, so fast that by all rights, they should have been flung out into intergalactic space long ago. It was as if there was some invisible additional mass providing extra gravitational pull, something that didn't emit light or interact with matter in any normal way except through gravity. This observation led to one of the greatest mysteries in modern physics: the dark matter problem. Some invisible substance making up roughly 85% of the matter in the universe permeates galaxies and holds them together through its gravitational influence. Without dark matter's additional gravity, galaxies would tear themselves apart as they rotate. But even accounting for dark matter, there remained a puzzle at the very center of galaxies, particularly at the center of our own Milky Way. Stars very close to the galactic core, within just a few light years of the center, moved at absolutely extraordinary speeds. We're not talking about the stately galactic rotation speed of 500,000 miles per hour. Stars near the very center race around their orbits at speeds exceeding 5 million miles per hour, more than 1% the speed of light. At such speeds, these stars complete full orbits in just a few years or decades, rather than the 225 million years it takes our Sun to orbit once. They trace elliptical paths so tight and so fast that astronomers can watch them visibly change position from year to year, can track them completing entire orbits within a human lifetime. The implication was staggering and unavoidable. Something extraordinarily massive and extraordinarily compact must lie at the exact center of our galaxy. These stars were behaving like iron filings caught in the field of a powerful magnet, or like planets orbiting a star, except the object they orbited was millions of times more massive than any star. But what could possibly account for such enormous mass in such a tiny volume? What kind of object could be millions of times heavier than our Sun, yet occupy a region of space smaller than our solar system? Early 20th century astronomers assumed that the dense concentration of stars near the galactic center could account for the rapid motions. Perhaps there was simply a very dense star cluster at the core, with millions of stars packed into a small volume. But as observational techniques improved and measurements became more precise, this explanation became increasingly untenable. The calculations didn't work. To explain the orbital speeds of the innermost stars, you would need to pack so many stars into such a small space that they would be constantly colliding and merging. The core would be an inferno of stellar collisions, producing distinctive signatures that weren't observed. Moreover, even this densely packed cluster of stars couldn't account for the full extent of the gravitational influence. There had to be something else, something far more massive, far more compact, and far stranger than any ordinary astronomical object. Something that could hide in plain sight at the center of our galaxy, invisible to our telescopes yet betrayed by the furious orbital dance of the stars in its gravitational grip. If not stars, if not gas, if not any form of matter we could see, then what could possibly hold these stars in such tight, rapid orbits? What kind of object could concentrate millions of solar masses into a space smaller than Mercury's orbit around our Sun? The answer would require a journey to the very edge of theoretical physics, to a prediction made decades earlier by Einstein's general relativity, but considered so exotic, so bizarre, that many physicists doubted such objects could actually exist in nature. The answer was a black hole. Not just any black hole, but a supermassive one, a gravitational monster weighing millions of times more than our Sun, compressed into a volume smaller than a single star. And it was hiding in the dark heart of our galaxy, waiting to be discovered. The center of our galaxy is a place of extraordinary violence and beauty, but for most of human history, it was utterly invisible to us. The problem is dust, vast clouds of interstellar dust particles that pervade the spiral arms of the Milky Way. These tiny grains, each smaller than a particle of smoke, are individually insignificant, but collectively they form an impenetrable barrier to visible light. Between Earth and the galactic center lie approximately 26,000 light-years of this dusty material. Light from stars at the core gets scattered and absorbed long before it reaches us, reduced by a factor of roughly 1 trillion. Trying to peer through this obscuring veil with ordinary optical telescopes is like trying to see through a wall of fog miles thick. The light simply cannot penetrate. This is why for thousands of years of human astronomy, the center of our own galaxy remained a mystery. Ancient astronomers could see the band of the Milky Way stretching across the sky, could trace out the constellations along its path, but the true center, the gravitational heart around which everything orbited, was hidden from view, concealed behind nature's most effective screen. The breakthrough came with the development of radio astronomy in the mid-20th century. Radio waves have much longer wavelengths than visible light, millions of times longer, and these longer waves can pass through dust clouds that completely block visible light. It's analogous to the way you can hear someone talking in another room even when you can't see them through the walls. Sound waves pass through barriers that light cannot. In the 1930s, Karl Jansky, an engineer working for Bell Telephone Laboratories, built the first radio antenna specifically designed to study cosmic radio waves. He discovered that a mysterious hiss of radio static came from the direction of the constellation Sagittarius, the direction of the galactic center. This was humanity's first detection of radio emission from the heart of our galaxy, though Jansky couldn't have known the true significance of what he'd found. Over the following decades, as radio telescope technology improved, astronomers built ever more sensitive instruments capable of mapping radio emission from the sky with increasing precision. They discovered that the galactic center was remarkably bright in radio wavelengths, emitting powerful radio waves that easily penetrated the obscuring dust and reached Earth. The critical discovery came in February 1974 when astronomers Bruce Ballack and Robert Brown used the Green Bank Interferometer in West Virginia to observe the galactic center with unprecedented resolution. They detected a very bright, very compact radio source at the precise gravitational center of the galaxy. They named it Sagittarius A, pronounced Sagittarius A star, with the asterisk denoting it as an exciting object, a modest bit of astronomical humor that stuck. What made Sagittarius A so extraordinary was not just its brightness, but its size, or rather, its remarkable lack of size. Radio observations could measure not just the intensity of the emission, but also the angular size of the emitting region. And Sagittarius A was tiny, incredibly, almost impossibly compact. The measurements showed that all that radio emission, powerful enough to be detected from 26,000 light-years away, came from a region no more than a few light-hours across, smaller than the diameter of our solar system. To put this in perspective, the distance from the Sun to Pluto is about 5.5 light-hours. All the radio emission from Sagittarius A came from a region smaller than the orbit of our outermost planet. This created an immediate puzzle. What could possibly be so bright yet so compact? Stars emit radio waves, but they're far too large and far too faint in radio wavelengths to match what was observed. Even the largest supergiant stars are measured in light minutes across, not light hours, and their radio emission is relatively weak compared to their visible light. A collection of stars packed into such a small volume would be constantly colliding, again producing signatures that weren't seen. Maybe it was a dense cloud of hot gas. But gas clouds need stars or some other energy source to heat them, and they tend to expand unless confined by powerful gravity. An ordinary gas cloud couldn't remain so compact or emit so powerfully without something else driving the process. Perhaps it was a pulsar, a rapidly spinning neutron star. Pulsars are incredibly compact and can be powerful radio sources, but pulsars emit radio waves in regular pulses as they rotate like cosmic lighthouses. Sagittarius A showed no such regular pulsations. Its emission was relatively steady, though with interesting flickering variations. Could it be a supernova remnant, the expanding debris shell from an exploded star? Supernova remnants are indeed powerful radio sources, but they expand rapidly and become larger over time. Sagittarius A remained compact and showed no signs of expansion. Every conventional explanation failed. The radio source was too bright, too compact, too steady, and too perfectly positioned at the gravitational center of the galaxy to be explained by any ordinary astronomical object or process. The observations built up a portrait of something unprecedented, a source smaller than our solar system, yet brighter in radio wavelengths than billions of stars combined. A source that sat precisely at the point around which 400 billion stars orbited. a source that emitted prodigious energy but remained invisible to optical telescopes. The name itself, Sagittarius A, became a placeholder for a profound mystery. The asterisk that Balick and Brown added to mark it as exciting proved prophetic. This wasn't just another radio source to catalogue and move on. This was something fundamentally new, something that would require expanding our understanding of physics and astrophysics to explain. Through the 1970s and 1980s, radio astronomers continued studying Sagittarius A, mapping its properties in ever greater detail. They discovered that it was actually composed of several components: Sagittarius A East, the remnant of a supernova explosion that occurred about 10,000 years ago; Sagittarius A West, a complex three-armed spiral of hot gas orbiting the center; and at the very heart of it all, the compact radio source they now called Sagittarius A. This innermost source, Sagittarius A Caus itself, remained enigmatic. It flickered and varied on timescales of minutes to hours, suggesting that the emission region was extraordinarily compact, so small that light could cross it in less than a day. It emitted not just radio waves, but also X-rays and infrared radiation, painting a picture of an environment of extreme energy and extreme physics. But radio waves alone couldn't reveal the full picture. To truly understand what Sagittarius A was, to prove the extraordinary hypothesis that was beginning to form in astronomers' minds, would require seeing through the dust in a different way. It would require infrared observations that could track the motions of individual stars in the immediate vicinity of this mysterious radio source. Because the key to understanding Sagittarius A lay not in observing the source itself, but in watching how it influenced the objects around it. The black hole's gravity would betray its presence through its effects on nearby stars, bending their paths, accelerating them to tremendous speeds, and inscribing its signature across the fabric of space-time itself. Something unimaginable was hiding at the precise center of the Milky Way, an object that defied every category of physics astronomers had available. An object too powerful to be a star, too concentrated to be gas, too compact to be any collection of ordinary matter, and too invisible to be anything they had encountered before. The hunt for the true nature of Sagittarius A would require new technology, decades of patient observation, and ultimately one of the most sophisticated imaging experiments ever attempted. But it would be worth it. Because at the end of that hunt lay proof of one of the universe's most exotic predictions, an object so strange that Einstein himself doubted they could exist in reality. A black hole, a supermassive black hole lurking in the dark heart of our cosmic home. The breakthrough that would transform Sagittarius A from a mysterious radio source into a confirmed supermassive black hole came not from radio astronomy, but from infrared observations, light with wavelengths longer than visible red light but shorter than radio waves. Like radio waves, infrared light can penetrate the dust that obscures the galactic center, though not as easily. This means that infrared telescopes can peer through the cosmic fog and see things that optical telescopes cannot: the individual stars moving in the immediate vicinity of the galactic center. And what those telescopes revealed was absolutely extraordinary. The story begins in the early 1990s, when two independent teams of astronomers began long-term programs to monitor stars near Sagittarius A. One team was led by Andrea Ghez at UCLA using the Keck Observatory in Hawaii. The other was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, using the Very Large Telescope in Chile. Both teams faced the same monumental challenge: capturing images sharp enough to track individual stars in the crowded environment of the galactic center, then following those stars year after year to map their motions. The technical challenges were formidable. Even with the largest telescopes on Earth Atmospheric turbulence blurs images, causing stars to twinkle and smearing out fine details. To overcome this, both teams pioneered the use of adaptive optics, sophisticated systems that measure atmospheric distortion hundreds or thousands of times per second and adjust the telescope's mirror to compensate, creating images nearly as sharp as if the telescope were in space. The effort paid off beyond anyone's expectations. By 1995, both teams had identified dozens of stars within a few light years of Sagittarius A, and they could measure the positions of these stars with exquisite precision. But the real revelation came as the years passed, and they could compare images taken at different times, watching how these stars moved against the background of more distant stars. The stars near Sagittarius A weren't just moving, they were racing. They traced elliptical paths at speeds that seemed to mock the very laws of orbital mechanics. Some were moving at more than 5 million miles per hour, more than 0.5% of the speed of light. At such velocities, these stars complete full orbits in time spans measured in years or decades, fast enough that their motion is visible from year to year, fast enough that a human astronomer can watch them complete multiple orbits in a single career. One star in particular captured the attention of astronomers worldwide. It was catalogued as S2 by the European team and S02 by the American team, different names for the same remarkable object. S2 is a blue giant star, roughly 15 times the mass of our Sun, burning with fierce brilliance. But its intrinsic properties weren't what made it special. What made S2 extraordinary was its orbit. S2 follows an elongated elliptical path that brings it within about 120 astronomical units of Sagittarius A closest. Approach? Roughly 4 times the distance from the Sun to Neptune. That might sound like a comfortable distance, but in the context of the galactic center, it means S2 plunges deep into the gravitational well of the central object, close enough that relativistic effects become not just measurable but dramatic. The orbital period of S2 is approximately 16 years. Think about that for a moment. Our Sun takes 225 million years to orbit the galactic center once. S2 completes a full orbit in less time than it takes a human child to reach adulthood. This isn't just fast, it's absurdly, almost incomprehensibly fast for an orbit around the galactic center. At its closest approach to Sagittarius A, which most recently occurred in May 2018, S2 reaches a peak velocity of roughly 5,000 miles per second, nearly 18 million miles per hour, or about 2.7% the speed of light. For comparison, the fastest spacecraft humans have ever built, the Parker Solar Probe, reaches peak speeds of about 430,000 miles per hour as it plunges near the Sun. S2 moves more than 40 times faster than our fastest spacecraft, and it does so not through rocket engines, but purely through gravitational acceleration. The environment S2 experiences at closest approach is difficult to comprehend. The tidal forces, the difference in gravitational pull from one side of the star to the other, are enormous, though not quite enough to tear the star apart. The star's light becomes gravitationally redshifted as it climbs out of the black hole's gravitational well, losing energy in the process. Time itself flows differently for S2 at periapsis, closest approach, than it does for us, observing from Earth, running measurably slower in the intense gravitational field. And most tellingly, S2's orbit precesses, its ellipse rotates slowly around the central point, tracing a rosette pattern rather than a closed ellipse. This orbital precession is a direct consequence of the extreme curvature of spacetime near the black hole, a fingerprint of Einstein's general relativity operating at its most extreme. But S2 is not alone. The decades of infrared monitoring revealed an entire population of stars in tight orbits around Sagittarius A. Astronomers have now identified and tracked dozens of these S-stars, each one providing an independent measurement of the central object's mass and a test of physics in the extreme environment near a supermassive black hole. Some of these stars have even shorter orbital periods than S2 star. S4714 holds the current record with an orbital period of just 12 years and a mind-boggling peak velocity of about 8% the speed of light, over 53 million miles per hour. At such speeds, relativistic effects are not subtle corrections but dominate the star's motion and appearance. These stellar races revealed something that radio observations alone could not conclusively prove. Whatever sits at the position of Sagittarius A must be extraordinarily massive and extraordinarily compact. The star's orbital velocities and periods allowed astronomers to calculate, with increasing precision, the exact mass of the central object using Kepler's laws of orbital motion. The same principles that govern the planets orbiting our Sun, just taken to an extreme. The calculated mass came out consistently, regardless of which star's orbit was used, approximately 4.3 million solar masses, give or take about 400,000 solar masses as the measurements improved over the years. 4,300,000 times the mass of our Sun, all concentrated at a single point at the center of the galaxy. But here's the crucial insight. These stars orbit through a region surrounding Sagittarius A that is empty. There is no visible object at the center, no cluster of stars, no glowing gas cloud, no anything that emits light. The stars race around a point in space that appears utterly dark in every wavelength of light we can observe. Yet their motion proves beyond any doubt that something massive occupies that dark point. The only explanation consistent with all the observations is that the central mass is contained within a volume smaller than the innermost stellar orbits, smaller than the S2's closest approach of 120 AU, smaller even than the much tighter orbits of stars like S4714. In fact, based on the radio size measurements of Sagittarius A itself, all that mass must be compressed into a region smaller than the orbit of Mercury around our Sun. There is no known configuration of normal matter, no collection of stars, no mass of gas, no any ordinary astronomical object that could pack 4.3 million solar masses into such a tiny volume without immediately collapsing under its own gravity into a black hole. Neutron stars, the densest stable objects known to physics, pack roughly 1.4 solar masses into a sphere only about 12 miles across. They represent matter compressed to the very edge of stability, where only the quantum mechanical pressure of neutrons prevents further collapse. But even neutron star matter has limits. Pack enough neutron stars together in a small space, and their combined gravity would overwhelm even neutron degeneracy pressure, forcing them to collapse. No force in physics can prevent such a collapse when you concentrate millions of solar masses into a region measured in light minutes. Not electron degeneracy pressure, which supports white dwarfs. Not neutron degeneracy pressure, which supports neutron stars. Not even the theoretical quark degeneracy pressure that might exist in the cores of the densest neutron stars. When enough mass concentrates in a small enough space, collapse to a black hole becomes not just possible, but inevitable. This is what the stellar racers told us. Their dance around the dark center wrote the proof in gravitational equations that could not be denied. Sagittarius A is a supermassive black hole, the first such object conclusively identified in our universe, and it sits at the gravitational heart of our own Milky Way galaxy. For their decades of patient observation, for tracking these stellar racers and proving the existence of the supermassive black hole at our galaxy's center, Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize in Physics, along with Roger Penrose for his theoretical work on black holes. The Nobel Committee recognized that their work had fundamentally changed our understanding of the galaxy we live in and confirmed one of the most exotic predictions of Einstein's theory of general relativity. But even with the mass measured, even with the existence of the black hole proven through the orbital dynamics of nearby stars, one profound question remained. Could we actually see the black hole itself? Could we photograph the darkness at the center, the shadow cast by an object from which light cannot escape? The answer would require building the largest telescope in history, not a single instrument, but a planet-spanning array of observatories working in perfect coordination. And when that array finally turned its attention to Sagittarius A, it would capture an image that seems to show the impossible, a photograph of darkness itself, framed by the light of doomed matter swirling toward oblivion.
How do you weigh something you cannot see, cannot touch, cannot reach?
How do you measure an object that exists in a state so extreme that the very concepts of surface and size become ambiguous? The answer lies in one of the universe's most fundamental principles. Gravity is universal, and its effects can be measured. You don't need to see an object to know its mass. You only need to observe how it influences other objects through its gravitational pull. This principle, first articulated by Isaac Newton in the 17th century and refined by Einstein in the 20th, has allowed astronomers to measure everything from the mass of planets to the mass of entire galaxy clusters. But nowhere has this technique been more dramatically applied than in measuring the black hole at the center of our galaxy. The method is conceptually simple, though extraordinarily challenging in execution. When an object orbits another under the influence of gravity, its orbital speed and the size of its orbit are directly related to the mass of the object it's orbiting. This relationship, encoded in Kepler's third law, provides a cosmic scale, a way to weigh celestial objects using nothing but patient observation and basic mathematics. For the planets in our solar system, we can measure their orbital periods, how long they take to go around the Sun, and their orbital distances, how far they are from the Sun, and from these two measurements alone, we can calculate the Sun's mass. The same principle works for moons orbiting planets, for binary stars orbiting each other, and for stars orbiting the galactic center. As of 2020, after more than 25 years of observations, the best estimate for the mass of Sagittarius A stands at 4.297 million solar masses. With an uncertainty of only about 60,000 solar masses, an astonishing precision of better than 1.5%, this makes Sagittarius A one of the most precisely measured black holes in the universe. To appreciate what this number means, consider that our Sun, for all its grandeur, would need to be multiplied by 4.3 million to equal the mass of Sagittarius A. If you could somehow place that many suns side by side, the line would stretch for about 3 billion miles, roughly the distance from the Sun to the orbit of Neptune multiplied by 30. But here's the truly staggering part. All of that mass, every ounce of those 4.3 million suns, is compressed into a volume incomprehensibly smaller than those 3 billion
Miles of suns would occupy the size of a
black hole. Is defined by its event horizon, also called the Schwarzschild radius, the boundary beyond which even light traveling at its maximum speed cannot escape the black hole's gravity. For a non-rotating Schwarzschild black hole, the radius of the event horizon is proportional to the mass. For Sagittarius A, with its mass of 4.3 million solar masses, this equation gives an event horizon radius of approximately 12 million kilometers, or about 7.5 million miles. That's roughly 17 times the radius of our Sun, or about 60 times the distance from the Earth to the Moon. Put another way, the event horizon of Sagittarius A is roughly the size of Mercury's orbit around the Sun. All those millions of solar masses, a mass equivalent to all the stars in a small galaxy, compressed into a sphere that would fit comfortably inside the orbit of the innermost planet in our solar system. The density implied by this compression defies human intuition. If you calculated the average density of Sagittarius A by dividing its mass by the volume enclosed by its event horizon, you would get roughly 1,000 kilograms per cubic meter, actually comparable to the density of air at sea level on Earth. this seems surprisingly low.
Almost mundane. But this number is deeply misleading.
The event horizon is not a physical surface. It's merely a point of no return, a mathematical boundary in space-time. The actual mass of the black hole isn't distributed throughout this volume like water in a balloon. Instead, according to general relativity, all the mass collapses to an infinitely dense point at the center called the singularity, where the laws of physics as we understand them break down completely. Between the singularity and the event horizon lies nothing. Empty space, or more accurately, space so profoundly warped by gravity that the concepts of space and time exchange roles. Once you cross the event horizon, moving forward in time becomes equivalent to moving toward the center. It becomes as inevitable as aging. You could no more avoid reaching the singularity than you could avoid living through the next second. This is what the stellar races revealed through their gravitational waltz. They mapped out the contours of space-time around the black hole with their orbits, each one a test particle tracing the curvature of space. And the picture they painted was of an object so dense, so massive and so compact that it represents the ultimate endpoint of gravitational collapse. No other explanation fits the observations. A cluster of stars dense enough to produce the observed gravitational effects would have a combined luminosity that would outshine the entire galactic center, and we see no such excess light. A cluster of stellar mass black holes or neutron stars would be unstable, with objects constantly colliding and merging, producing bursts of gravitational waves and other signatures that aren't observed. A hypothetical ball of dark matter would need to be so dense that it would itself collapse
into a black hole within a very
short time, the only stable configuration consistent with 4.3 million solar masses in a region smaller than Mercury's. Orbit is a single supermassive black hole. This conclusion is further reinforced by the radio and X-ray observations of Sagittarius A itself. The compact radio source, remember, is smaller than our solar system, much smaller than the orbits of even the innermost observed stars. The flickering X-ray emissions show variability on timescales of minutes, which means the emission region must be smaller than a few light minutes across, again, much smaller than the stellar orbits. Everything points to the same conclusion, a supermassive black hole. Its event horizon, a dark sphere about 15 million miles across, sits at the precise gravitational center of the Milky Way galaxy. It neither creates nor destroys gravity. It simply is gravity, concentrated and made manifest in its most extreme form. For humanity, this discovery represented a profound moment of understanding. For the first time, we had not just detected but precisely measured an object that represented the ultimate extreme of physics, a place where matter, space, and time itself are pushed beyond the breaking point of our everyday understanding. And we had done it by using the black hole's own gravity as an instrument, reading its signature in the motions of stars, using celestial mechanics first worked out by Johannes Kepler in the 17th century and Isaac Newton in the 18th, refined by Einstein in the 20th, and brought to exquisite precision by 21st century technology and human perseverance. The universe had finally taken its own measure. And at the heart of our cosmic home, we had found a monster, a beautiful, terrible, precisely quantified monster that had been hiding there all along, patiently waiting to be discovered. But measuring the monster was only the beginning. The next challenge would be even more audacious, actually seeing it, capturing its image, photographing the shadow it casts against the glow of infalling matter. On May 12, 2022, at simultaneous press conferences held around the world, scientists revealed something that should be impossible, a photograph of Sagittarius A, the supermassive black hole at the center of our galaxy. The image showed exactly what Einstein's equations predicted a black hole should look like, a glowing ring of orange-yellow light encircling a dark, circular shadow. The ring wasn't uniform. It had bright spots and dimmer regions, showing the chaotic swirl of matter racing around the black hole at a significant fraction of light speed. And at the center, defining the whole structure, sat perfect darkness, the shadow of the event horizon itself, from which no light can escape. This was only the second black hole ever photographed, following the historic 2019 image of the supermassive black hole at the center of the galaxy M87. But in many ways, imaging Sagittarius A was more technically challenging and more scientifically significant. This was our black hole, the gravitational anchor of our cosmic home, and capturing its portrait required pushing the boundaries of observational astronomy to their absolute limits. The instrument used to capture this image was the Event Horizon Telescope, EHT, but calling it a telescope barely captures the audacity of the project. The EHT is actually a global network of radio telescopes scattered across 4 continents, in Hawaii, Arizona, Chile, Antarctica, Spain, and Mexico, all working together as a single instrument through a technique called Very Long Baseline Interferometry, or VLBI. The principle behind VLBI is as elegant as it is complex. The resolving power of a telescope, its ability to see fine details, is limited by its diameter. A larger telescope can see finer details than a smaller one, which is why astronomers constantly build bigger and bigger dishes. But there's a practical limit to how large you can make a single dish. The largest single-dish radio telescope in the world, China's FAST telescope, is 500 meters, 1,640 feet across, requiring an entire valley to house it. To image a black hole's event horizon from 26,000 light-years away requires
Angular resolution measured in
micro-arc seconds, the equivalent of being able to see an orange sitting on the surface of the moon from Earth, or reading a newspaper in New York from Paris. No single telescope ever built comes remotely close to this capability. But here's the clever part. You don't need to build a single, enormous dish. Instead, you can combine the signals from multiple smaller dishes scattered across a large area, using the distance between them as your effective telescope diameter. If you coordinate telescopes separated by thousands of miles, you can create a virtual telescope with an effective diameter of thousands of miles. This is VLBI, using the Earth itself as the telescope. The EHT combines 8 major facilities to create a virtual telescope nearly as large as the Earth, with an effective diameter of about 10,000 kilometers, 6,200 miles, and an angular resolution of about 20 micro-arc seconds. This is just barely good enough to resolve the event horizon of Sagittarius A. But the technical challenges of actually doing this border on the absurd. Each telescope in the array collects enormous amounts of data, several petabytes per observing session, equivalent to the entire data content of hundreds of thousands of high-definition movies. This data must be recorded with nanosecond precision, time stamped using atomic clocks at each site, then physically shipped to central processing facilities where supercomputers spend months correlating the signals. You can't simply send the data over the internet. There's too much of it, and it arrives too fast. Hard drives filled with data are literally flown or shipped from remote sites like the South Pole Telescope to processing centers, where they're fed into specialized supercomputers that spend months performing the correlation. The correlation process looks for patterns in the radio waves detected at different telescopes. When a wavefront from the black hole reaches Earth, it arrives at different telescopes at slightly different times because they're in different locations. By precisely measuring these tiny time differences and combining the data, the system can reconstruct what the source must look like, building up an image from radio frequencies the way your eye builds an image from visible light. But there's another profound challenge unique to Sagittarius A. It changes rapidly. The M87 black hole which the EHT imaged first, is truly supermassive, 6.5 billion solar masses, about 1/500 times more massive than Sagittarius A. Because of its enormous size, matter takes weeks to complete an orbit near its event horizon, so the appearance of the surrounding material stays relatively constant over the course of a night's observation. You can treat it as essentially static, take a single long exposure, and get a clear image. Sagittarius A is much smaller, and matter orbits it much faster, completing a full orbit in just 20 to 30 minutes. This means the appearance of the glowing material around the black hole changes dramatically even during a single night's observation, like trying to photograph a hyperactive puppy that won't hold still. Imagine trying to take a long exposure photograph of a subject that completely rearranges itself every half hour. You'd end up with a blurry mess, a superposition of many different appearances blended together. This is exactly the problem the EHT team faced with Sagittarius A. The solution required developing entirely new data analysis algorithm. The team had to take thousands of individual snapshots over several nights of observation and then use sophisticated computer models to figure out what the average structure looked like, what features were stable and which were transient flickering. It required running millions of simulations of black hole accretion disks, comparing them to the data, and using machine learning algorithms to extract the underlying structure from the chaotic variability. The observational campaign took place over several nights in April 2017, using 8 telescopes: the Atacama Large Millimeter, Submillimeter Array, ALMA in Chile, the Atacama Pathfinder Experiment Apex in Chile, the IRAM 30-meter telescope in Spain, the James Clark Maxwell Telescope in Hawaii, the Large Millimeter Telescope in Mexico, the Submillimeter Array in Hawaii, the Submillimeter Telescope in Arizona, and the South Pole Telescope in Antarctica. These telescopes observed at a wavelength of 1.3 millimeters in the radio part of the electromagnetic spectrum. This wavelength was chosen carefully. It's short enough to provide the necessary angular resolution, but long enough to penetrate the interstellar gas and dust between Earth and the galactic center, and long enough that interstellar scattering doesn't blur the image too much. After 5 years of data processing, algorithm development, and careful verification, the team finally had their result, an image showing a ring of emission about 52 micro-arc-seconds in diameter, with a dark, circular region in the center about 20 micro-arc-seconds across. The ring structure is created by photons, particles of light, emitted by hot gas orbiting the black hole. Some of these photons escape to space, allowing us to see them. But near a black hole, gravity is so strong that it bends the paths of photons, creating extraordinary optical effects. Light emitted from behind the black hole can be bent around it, making the backside visible. Light emitted near the event horizon can orbit the black hole multiple times before escaping, creating a series of ever fainter photon rings. The result is that the black hole appears surrounded by a ring of light, actually a sphere of light, when seen in 3 dimensions, but appearing as a ring in projection. And the black hole itself appears as a dark circle larger than the actual event horizon, because the gravity is so strong that it captures photons passing nearby, even if they didn't originate inside the event horizon. This enlarged shadow is about 2.6 times the diameter of the event horizon itself for a non-rotating black hole, or somewhat larger for a rotating one. For Sagittarius A, with an event horizon diameter of about 24 million kilometers, the shadow should appear about 52 micro-arc-seconds across as viewed from Earth, exactly what the EHT observed. The measurement agreed with Einstein's predictions to within the measurement uncertainties. The image also showed asymmetries. The ring was brighter on one side than the other. This brightness asymmetry is created by relativistic beaming. Matter orbiting the black hole at close to light speed emits light that gets beamed forward in its direction of motion, like the headlight of a train. The side of the disk where matter is moving toward us appears brighter than the side where it's moving away, creating the observed asymmetry. These subtle features encode information about how the black hole is spinning, how matter flows into it, and how magnetic fields shape the accretion process. Scientists continue to analyze the data, extracting every possible piece of physics from those micro-arc seconds of glowing gas. The universe had finally posed for a selfie, or more precisely, had allowed us to photograph its own darkness. The image of Sagittarius A represents a triumph of human ingenuity, international cooperation, and scientific perseverance. It required technology that didn't exist when the project began, algorithms that had to be invented specifically for this purpose, and hundreds of scientists working together across decades, but perhaps more than that. The image represents a philosophical milestone. For centuries, we've known the universe through indirect evidence, through inference and calculation. We've deduced the existence of atoms without seeing them, calculated the mass of planets from their gravitational tugs, and inferred the presence of dark matter from its gravitational effects. But here, finally, was a direct observation of one of the universe's most extreme objects. We had photographed the darkness at the center of our galaxy. We had captured visual proof that Einstein's most exotic prediction that gravity could become so
strong it tears a hole in space-time itself was not just
mathematically possible but physically real, that a photograph of Sagittarius A
wasn't just an image, it was evidence.
Evidence that black holes exist. Evidence that general relativity works even in its most extreme regime. Evidence that the monster at the center of our galaxy is precisely what decades of observation suggested it must be, and the image was beautiful. Against all odds, the universe's most violent, most extreme, most alien environment created a structure of almost perfect circular symmetry. The monster wore a halo of light. The black hole at our galaxy's center doesn't just bend space, it warps time itself. And nowhere is this more apparent than in the behavior of light escaping from near the event horizon. This might sound like science fiction, but it's precisely measurable science fact, verified every time a star like S2 makes its closest approach to Sagittarius A. The observations reveal something profound. Clocks run at different rates depending on how deep they are in a gravitational field. Time itself is not absolute but relative, flowing at different speeds in different environments. This phenomenon, called gravitational time dilation, is one of the central predictions of Einstein's general theory of relativity. The theory tells us that gravity is not a force pulling objects together, but rather a curvature of space-time caused by the presence of mass and energy. Massive objects like stars and black holes create wells in the fabric of space-time, and other objects roll along the curved surface of these wells. But the curvature affects more than just spatial paths, it affects time itself. The deeper you go into a gravitational well, the more slowly time passes relative to regions farther away. This isn't an illusion or a measurement artifact, it's a real, physical difference in the rate at which time flows. For most everyday situations, this effect is vanishingly small. On Earth's surface, time runs about 1 part in 10 billion slower than it would in empty space, far from any mass. You'd need extraordinarily precise clocks to measure this difference. Though it has been done, atomic clocks taken to the top of mountains measurably tick faster than identical clocks at sea level. But near a supermassive black hole, the effect becomes dramatic. As S2 approaches its closest point to Sagittarius A, diving deep into the gravitational well, time for the star slows relative to distant observers watching from Earth. If you could somehow stand on S2 and look out at the universe, you'd see events in the outside universe speeding up, while we on Earth watching S2 would see time on the star slowing down. The most direct observational signature of this time dilation is gravitational redshift. Light is a wave oscillating at a particular frequency. When that light is emitted deep in a gravitational well and then climbs out, it loses energy, not because it's absorbed by anything, but because it's climbing against gravity. Since the energy of light is proportional to its frequency, losing energy means the light's frequency decreases, shifting toward the red end of the spectrum, hence redshift. For S2 at its closest approach to Sagittarius A, detailed spectroscopic observations reveal that the star's light is gravitationally redshifted by about 200 kilometers per second, meaning the wavelength
of every photon is stretched by about 1 part in 1/500 as it climbs out of the black hole's
gravitational well. This is not due to the star's motion, which produces a separate Doppler shift that can be corrected for, but is a purely gravitational effect. This redshift is exactly what Einstein's equations predict. The mathematics is straightforward once you know the mass of the black hole and the closest approach distance. The fact that the observed redshift matches the predicted value to within measurement uncertainties is powerful confirmation that general relativity correctly describes gravity even in this extreme environment. But gravitational redshift is just one manifestation of time dilation. The effect goes deeper, literally. Imagine you are watching someone fall toward the event horizon of Sagittarius. As they got closer and closer to that boundary, time dilation would become more and more extreme. You'd see them moving more and more slowly, their clock ticking more and more leisurely compared to yours. At the event horizon itself, time dilation becomes infinite. A clock at the event horizon, as viewed from far away, would appear to stop completely. This creates one of the most bizarre consequences of black hole physics. From the perspective of a distant observer, nothing ever actually crosses the event horizon. You'd see an infalling object get closer and closer, moving more and more slowly, its light getting more and more red-shifted, until finally it fades from view, not because it crossed the horizon, but because its light gets stretched to infinite wavelength and infinite dimness. But from the perspective of the infalling object, something entirely different happens. Time continues to flow normally from your own perspective. You don't notice yourself slowing down. You would cross the event horizon in a finite amount of your own time, perhaps a few seconds or minutes, depending on the size of the black hole and your trajectory. There would be no special marker, no physical membrane, no sudden transition, just a mathematical point of no return that you'd pass without immediate notice. This is symmetry, the fact that distant observers never see you cross, while you experience crossing in finite time, is not a contradiction, but a profound insight into the nature of time itself. Time is not a universal backdrop against which events unfold. It's part of the geometry of space-time, and different observers moving on different trajectories through space-time experience it differently. Near Sagittarius A, these effects are dramatic enough to be measured with current technology. In 2018, as S2 passed through periapsis, multiple research teams measured the gravitational redshift and confirmed it matched Einstein's predictions. In 2020, they measured additional relativistic effects, including the Schwarzschild precession of S2's orbit, the fact that the orbit itself rotates slightly with each passage, tracing a rosette pattern rather than a closed ellipse. All of these observations tell the same story. Space-time near Sagittarius A is profoundly curved, and time flows at different rates depending on your position in that curved geometry. But perhaps the most poignant implication is what it would mean for an astronaut falling toward the black hole. From Earth, we'd watch them slow down, see their clock tick more and more slowly, see their light get redder and redder as time dilation increased. They'd appear frozen at the edge of the horizon, locked in time forever from our perspective. But from their perspective, they'd fall through the horizon and hit the singularity at the center in a brief, finite span of their own time, perhaps just seconds or minutes. In those final moments, they'd experience tidal forces growing without limit, space-time curvature approaching infinity, and the breakdown of all physics as we understand it. You could never save them, even in principle. Once they cross the horizon, they're in a region of space-time from which no signal can ever return. They're cut off from the rest of the universe, isolated behind an absolute barrier, and from their perspective, they'd see the entire future history of the outside universe play out in fast forward as they fell, watching stars burn out, galaxies collide, and the universe evolve toward its ultimate fate, all in the span of moments by their own clock. This is the deep strangeness that lives at the heart of our galaxy. Time itself becomes a variable, flowing at different rates, creating impossible paradoxes and revealing that our intuitive understanding of now and later breaks down completely in strong gravity. The black hole doesn't just devour matter and light, it devours time itself, or more accurately, reveals that time is not the absolute,
uniform cosmic clock we imagine it to be.
It's malleable, relative, part of the flexible geometry of the universe itself. And as time slows and distorts, space itself begins to warp in ways that defy our everyday geometric intuition. Near the event horizon, space doesn't just curve, it twists, coils, and folds back on itself, creating effects so strange that even Einstein initially doubted they could be real. If you could somehow watch S2's orbit from above the galactic plane, suspended in space with a view of the galactic center over millions of years, you would see something beautiful and strange. The star's elliptical orbit doesn't close back on itself. Each time around, the ellipse rotates slightly, so that over many orbits the path traces out a flower-like pattern, a geometric rosette of overlapping ellipses, each one slightly rotated from the last. This effect is called orbital precession, and it's one of the most elegant proofs that space-time near Sagittarius A is curved in exactly the way Einstein predicted. Orbital precession isn't entirely unfamiliar. Mercury, the innermost planet in our solar system, exhibits the same phenomenon. Its elliptical orbit rotates by about 574 arcseconds per century. For a long time, this was a mystery. Newtonian gravity predicted that Mercury should trace a closed ellipse, returning to exactly the same positions with each orbit. The observed precession didn't match Newton's theory. Most of Mercury's precession, about 531 arcseconds per century, can be explained by the gravitational perturbations
of other planets tugging on Mercury's orbit.
But there remained an unexplained residual of about 43 arcseconds per century that no amount of adjustment to Newton's theory could account for. This tiny discrepancy was one of the great unsolved problems of 19th century astronomy. Then in 1915, Einstein published his general theory of relativity, and one of the first things he calculated was Mercury's orbit using his new equations. When he included the curvature of spacetime around the Sun, out popped an additional 43 arcseconds per century of precession, exactly matching the observations. This was one of the first major confirmations that Einstein's theory was not just mathematically elegant, but physically correct. Near Sagittarius A, the same effect occurs, but vastly amplified. The space-time curvature near a supermassive black hole is millions of times more intense than near our Sun. S2's orbit precesses not by tiny arcseconds per century, but by measurable degrees with each orbit, about 12 arcminutes per orbit, or roughly 1/5 the apparent diameter of the full moon. Measuring this precession requires extraordinary precision. Astronomers need to track S2's position over multiple complete orbits, which means observations spanning several decades given the star's 16-year period. They need to correct for the motion of Earth around the Sun, the motion of the Sun around the galactic center, the effects of other nearby stars, interstellar dust absorption, atmospheric distortion, and a host of other effects. The breakthrough came with the development of adaptive optic systems and laser guide stars. These technologies allow ground-based telescopes to achieve angular resolution approaching that of space-based observatories by correcting for atmospheric turbulence in real time. With these systems, astronomers can measure S2's position to within a few hundred micro-arc seconds, roughly equivalent to measuring the width of a human hair from 1,000 kilometers away. By 2020, S2 had been tracked through one complete orbit since high-precision observations began, giving astronomers their first chance to measure the orbital precession directly. The gravity collaboration, using the Very Large Telescope's interferometric capabilities, measured the precession and found it agreed with general relativity to within their measurement uncertainties. This
wasn't just a confirmation that Einstein
was right, it was a test of general relativity, in a regime far more extreme than had ever been tested before. Mercury orbits in a region where space-time is only very slightly curved, where relativistic effects are tiny corrections to Newtonian gravity. S2 orbits in a region where space-time is profoundly curved, where relativistic effects dominate and Newtonian gravity is merely an approximation. The fact that Einstein's century-old equations, developed without any knowledge of black holes or neutron stars or any of the extreme astrophysical objects we now know exist, correctly predict the motion of S2 in this extreme environment is a testament to the theory's profound nature. But the orbital precession tells us something deeper than just confirming relativity. It maps out the geometry of spacetime itself. Each orbit that S2 traces is a geodesic, a path of shortest distance through curved spacetime. The fact that these geodesics don't close, that each orbit traces a slightly different path, reveals the specific curvature of spacetime around the black hole. Think of it this way: on a flat surface like a tabletop, if you draw a closed curve, like an ellipse, and then try to draw another one starting from the same point, you'd trace exactly the same path. But on a curved surface like a sphere, curves behave differently. Draw a closed loop on a globe, then try to draw another one from the same starting point. The second loop will naturally rotate compared to the first because of the sphere's curvature. Space near. Sagittarius A is curved not in 2 dimensions like a sphere, but in 4 dimensions, 3 of space and 1 of time, in ways that are impossible to visualize directly. But the effect is analogous. Closed orbits don't stay closed because space itself is curved. The orbital precession is a direct measure of that curvature. For a spherically symmetric, non-rotating black hole, the Schwarzschild solution, these equations predict a specific amount of orbital precession. For a rotating black hole, the Kerr solution, the predictions are slightly different. By measuring the precession precisely, astronomers can not only confirm that relativity is correct, but also determine whether Sagittarius A is rotating, and if so, how fast? Current observations suggest that Sagittarius A is rotating, perhaps at a significant fraction of its maximum possible spin rate, though measurements are still being refined. A rotating black hole drags spacetime around with it, creating an effect called frame dragging or the lens-Thirring effect. Near the black hole, space itself is rotating, forced into a swirling motion by the black hole's spin. This adds additional complexity to the orbital precession and creates unique observational signatures. The imagery of the relativistic flower, the rosette pattern, traced out by S2's orbit is more than just a pretty picture. It's a map of space-time geometry, a visible record of how mass and energy curve the fabric of reality. Each petal of the flower is an orbit, each rotation a testament to Einstein's insight that gravity is geometry. Even in the universe's most chaotic place, where matter spirals toward oblivion and space and time twist beyond everyday comprehension, the laws of physics write poetry. The dance of S2 around Sagittarius A is not random chaos, but elegant mathematics made visible, differential geometry expressed in stellar motion. And there's something deeply satisfying in this, that we can observe an object 26,000 light-years away, watch its motion with painstaking care, and from that motion deduce the precise curvature of spacetime at the heart of our galaxy. That we can test Einstein's century-old equations in a regime he never imagined and find them still holding true. The flower of precessing orbits doesn't just bloom in space, it blooms in the human mind as understanding, as the mathematical elegance of general relativity meeting and matching the observed reality of nature. Space near Sagittarius A isn't just curved, it's sculpted, shaped by gravity into forms that challenge our ability to visualize but yield beautifully to mathematical description. And as we peer deeper into this gravitational sculpture, as our measurements become more precise and our theoretical understanding more sophisticated,
new insights continue to emerge. The monster at the center doesn't just sit there, passive and inert.
It's an active, dynamic object, shaping the space around it, influencing the evolution of the entire galaxy, and teaching us profound lessons about the fundamental nature of reality itself. Sagittarius A is not unique. It's not an anomaly or a cosmic accident. It's an example, perhaps the closest and best-studied example, of a phenomenon that appears to be universal. Every large galaxy in the observable universe seems to harbor a supermassive black hole at its center. This realization has transformed our understanding of how galaxies form and evolve. Black holes aren't just end-stage objects, the final corpses of dead stars. They're architects, sculpting galaxies, regulating star formation, and playing a crucial role in the large-scale structure of the universe. The evidence for ubiquitous, supermassive black holes has accumulated steadily over the past 3 decades. Astronomers have now measured the masses of supermassive black holes in hundreds of galaxies using the same techniques employed for Sagittarius A, tracking the motion of stars or gas clouds near galactic centers, measuring orbital velocities and calculating the central mass. What they've found is remarkable. There's a consistent relationship between the mass of a galaxy's central black hole and the properties of the galaxy as a whole, particularly the mass of the galaxy's central bulge,
and the velocity dispersion of stars in that bulge.
This relationship, called the M-sigma relation, shows that black hole mass scales predictably with galaxy mass. For a typical large galaxy, the central black hole contains about 0.1% to 0.2% of the total mass of the galaxy's bulge. This sounds like a small fraction, but it represents billions or even trillions of solar masses for the most massive galaxies. The supermassive black hole at the center of the giant elliptical galaxy M87, for example, the first black hole to be photographed by the Event Horizon Telescope, weighs approximately 6.5 billion solar masses, about 1,500 times more massive than Sagittarius A. The most extreme known supermassive black holes tip the scales at tens of billions of solar masses. TON 618, a quasar more than 10 billion light-years away, harbors a black hole estimated at 66 billion solar masses, more than 15,000 times the mass of Sagittarius A. And these are not just black holes, they're ultramassive black holes, objects whose event horizons are larger than the orbit of Neptune, whose gravitational influence extends across light-years. Why should there be such a consistent relationship between black hole mass and galaxy properties? This is one of the deepest questions in modern astrophysics, and the answer seems to involve a feedback loop between black holes and the galaxies that host them. When matter falls into a supermassive black hole, it doesn't simply disappear. Before crossing the event horizon, the infalling material forms an accretion disk, a swirling disk of gas heated to millions of degrees by friction and tidal forces. This disk emits enormous amounts of radiation, sometimes outshining the entire galaxy. Magnetic fields threading through the disk can launch powerful jets of material at near-light speed, shooting out along the black hole's rotation axis for thousands or even millions of light-years. These processes pump energy into the surrounding galaxy. The radiation can heat gas clouds, preventing them from cooling and collapsing to form new stars. The jets can blow gas out of the galaxy entirely, removing the raw material for star formation. This is called AGN feedback. AGN stands for Active Galactic Nucleus, the bright region powered by an accreting supermassive black hole. And it appears to be crucial in regulating how galaxies grow. Without this feedback, galaxies would convert their gas into stars too efficiently, creating more massive, more metal-rich galaxies than we actually observe. The supermassive black holes act as thermostats, preventing runaway star formation and maintaining galaxies in a balanced state. But this raises a chicken and egg question. Did the black holes form first and then build galaxies around them? Or did galaxies form first and then create black holes at their centers? The current thinking is that it's probably both, in an intricate dance of coevolution. Early in cosmic history, perhaps just a few 100 million years after the Big Bang, the first black holes likely formed from the direct collapse of massive gas clouds or from the deaths of the very first generation of massive stars. These seed black holes, perhaps ranging from hundreds to millions of solar masses, grew rapidly by accreting gas and by merging with other black holes when their host galaxies collided. Meanwhile, the black holes influenced the evolution of their host galaxies through the feedback processes described above. Galaxies and their central black holes grew together, their fates intertwined, their evolution coupled through the exchange of matter and energy. The details of this coevolution remain an active area of research. We observe supermassive black holes at such early times in cosmic history, less than 1 billion years after the Big Bang, that it's challenging to explain how they grew so massive so quickly. We observe the effects of AGN feedback throughout cosmic history, but the precise mechanisms and their quantitative effects are still being worked out. We're discovering new relationships between black holes and their host galaxies, suggesting connections we don't yet fully understand. But one thing is clear: supermassive black holes are not passive residents of galactic centers. They're active participants in cosmic evolution, shaping the universe around them in profound ways. There's a philosophical dimension to this as well. The black hole at the center of the Milky Way, that invisible monster we've been tracking through this entire narrative, is not an intruder or a threat. It's an integral part of our galaxy's structure and history. The Milky Way as we know it, with its spiral arms, its stellar populations, its distribution of gas and dust, has been shaped by the presence of Sagittarius A over billions of years. In a very real sense, the black hole didn't form inside the galaxy formed around it. Or more accurately, both emerged together from the chaotic conditions of the early universe, their evolution intertwined from the beginning. Could the Milky Way exist without Sagittarius A?
Probably in some form.
The black hole's mass is tiny compared to the total mass of the galaxy, about 0.05% of the Milky Way's stellar mass, and a vanishingly small fraction of the total mass, including dark matter. It doesn't hold the galaxy together through its gravity. That's the job of the distributed dark matter halo, but the galaxy's detailed structure, its star formation history, the chemistry of its stars, the distribution of its gas, all of these have been influenced by the black hole's presence and activity over cosmic time. Remove Sagittarius A from the Milky Way's history, and you'd have a different galaxy, perhaps subtly, perhaps dramatically, and there's a deeper implication. If every galaxy harbors a supermassive black hole, and if these black holes play crucial roles in galactic evolution, then black holes are not rare exotic objects, but fundamental components of cosmic structure. They're as important to understanding the universe as stars, galaxies, and dark matter. The universe builds black holes wherever it can, whenever enough mass concentrates in a small enough region. And once created, these black holes reshape their environments, influence the evolution of structure around them, and leave their fingerprints on the cosmos itself. Perhaps most remarkably, from our vantage point, 26,000 light-years from the Milky Way's center, we're in an ideal position to study one of these objects. Sagittarius A is not the most massive supermassive black hole, nor the most active, but it's ours, close enough to study in detail, quiet enough not to blind us with radiation, massive enough to produce measurable relativistic effects. It's the perfect laboratory for studying black hole physics, testing general relativity, and understanding the role of black holes in cosmic evolution. And every observation, every measurement, Every image adds another piece to the puzzle of how these objects work and what they mean for the universe as a whole. The black hole doesn't just sit at the center of the Milky Way. In a sense, it sits at the center of our curiosity about the cosmos, a focal point for questions about the nature of gravity, the fate of matter, the evolution of galaxies, and the fundamental structure of space-time itself. We've measured its mass with exquisite precision. We've photographed its shadow. We've watched stars dance around it in relativistic waltzes. We've seen time dilate and space curve in its presence. But there's still so much we don't understand.
How did it form? How fast is it spinning?
What happens to information that falls into it? What existed before it, and what will remain after it? These questions drive astronomical research forward, pushing the boundaries of technology and theory. And at the heart of these questions sits Sagittarius A, the monster at the center, the dark heart of our cosmic home, the object that shouldn't exist but does, patiently waiting at the bottom of its gravitational well for us to understand it better. We began in darkness, with an invisible object at the heart of the Milky Way, detectable only through its gravitational influence on the stars that orbit it. We've emerged from that journey with something remarkable, not just knowledge of what that object is, but an understanding of how it shapes the galaxy around it and what it reveals about the fundamental nature of reality. At the heart of our galaxy, something devours light and gives meaning to it. This paradox that an object defined by its absolute darkness can be understood through careful observation, precise measurement, and theoretical insight encapsulates the entire enterprise of science. We cannot see the black hole directly, but we can see its effects. We cannot reach it, but we can measure it. We cannot visit it, but we can understand it. Sagittarius A is simultaneously a destroyer and a creator. It destroys in the most literal sense. Anything crossing its event horizon is lost forever, removed from the universe we can observe, its information, as far as we know, erased from reality. The tidal forces near the singularity would tear apart any structure, reducing atoms, molecules, even subatomic particles to their constituent parts before pulling them into the infinitely dense center. But it's also a creator. The energy released by matter falling into the black hole can power jets and outflows that trigger star formation in distant regions of the galaxy. The gravitational influence of the black hole helps shape the galaxy's structure, maintaining the central bulge, influencing the orbits of stars, contributing to the overall architecture of the Milky Way. And perhaps most fundamentally, the very processes that form supermassive black holes in the early universe may be intertwined with the processes that form galaxies themselves. Without Sagittarius A, the Milky Way wouldn't exist, at least not in the form we know, with its specific distribution of stars and gas, its history of star formation and chemical evolution, its structure and dynamics. The black hole has been a silent partner in our galaxy's evolution for billions of years, shaping the cosmic environment in which our solar system formed, our planet coalesced, and our species evolved. There's a humbling beauty in this realization. Every atom in your body was forged in the nuclear furnaces of stars, then scattered into space when those stars exploded. Those atoms drifted through the galaxy, influenced by gravitational fields, including the distant tug of Sagittarius A, until they collected into the cloud from which our solar system formed. The galaxy's structure, shaped over billions of years partly by the presence of the central black hole, created the conditions for our sun to form where and when it did. In this sense, the black hole at the center of the Milky Way is part of your story, part of the chain of causation that led to your existence. It's a thread in the cosmic tapestry, invisible but essential, connecting you to the largest structures in the universe. And yet, for all we've learned, profound mysteries remain. What actually happens at the singularity where density becomes infinite and our equations break down, does information that falls into a black hole truly disappear, violating quantum mechanics, or is it somehow preserved? How exactly did the first supermassive black holes form in the early universe? How do stellar mass black holes merge to form larger ones? And what is the distribution of intermediate mass black holes? These questions represent the frontier of physics, the boundary where our current understanding gives way to speculation and
new theories.
Black holes occupy this liminal space between what we know and what we're still trying to understand, making them perfect subjects for continuing exploration. Perhaps the most profound lesson from our study of Sagittarius A is this: the universe's darkest places are not voids of destruction, but engines of creation itself. They're laboratories where nature tests physics at its limits. They're archives encoding the history of galaxy formation and evolution. They're teachers showing us through their extreme behavior the deep connections between gravity, space, time, matter, and energy. Because even where light ends, at the event horizon of a black hole, where escape becomes impossible and causality breaks down, curiosity continues. The human drive to understand, to measure, to explain doesn't stop at comfortable boundaries. It pushes into the darkness, builds telescopes the size of planets to photograph shadows, tracks stars across decades to measure invisible masses, develops new mathematics to describe what happens when space-time itself tears. This is the legacy of Sagittarius A. It challenges us to think deeper, to look more carefully, to push the boundaries of what's possible. It sits at the center of the Milky Way, and in doing so, it sits at the center of some of the deepest questions we can ask about reality. The monster at the center has been revealed not as something to fear, but as something to study, to understand, and ultimately to appreciate as an essential part of the cosmos we inhabit. It's a reminder that the universe is stranger, more beautiful, and more comprehensible than we might have imagined. That darkness, properly studied, illuminates. That the invisible, carefully measured, becomes known, and that at the heart of everything, all the stars, all the planets, all the swirling galaxies and cosmic structures, lies not just matter and energy, but meaning waiting to be discovered. The monster at the center guards no treasure except understanding itself. And that perhaps is the most valuable treasure of all.